All right, so this is the second lecture on combinational logic design. In the first one, we talked about encoders, decoders, tri-state buffers. And now we are going to be talking about multiplexers, demultiplexers, adders, and comparators. Multiplexers is where we'll start, and this happens to be one of my favorite digital design components. And the reason why it is my favorite is because it is elegant, it is versatile. I can use this to solve many problems. So I can use this for many applications. So let's start with answering a few questions. Multiplexer, what is it used for? The name itself gives it away, right? Multiplexing. I am trying to select. The answer is select one input from many inputs. If I have 4 inputs, I'm trying to select one of them. If I have 8 inputs, I'm trying to select one of them. No matter how many inputs I have, I'm selecting one of them. So that means it is sort of a many to one design, right? So many come in, but only one goes out. So you can think of a multiplexer or multiplexer as a selector. I'm trying to select one from many. All right, what are its inputs? Well, it actually has two types of inputs. The first one is I need some inputs to be select lines. And I need the inputs themselves. And I'm going to call that data inputs. So there is a distinction. The types of inputs could be select inputs or it could be data inputs. What are its outputs? Well, only one output because we said one out of many. So one output, one data output. So this is how it's supposed to work. Depending on which input you select using the select inputs, one of these data inputs will go to the output. As simple as that. Maybe I can write that statement here. Depending on which select inputs you use, not use, you make active, output will equal one of data inputs. That's it. That's the core. What is a symbol? Well, it should have some sort of many to one indication, right? So that symbol is typically this. Many, long line, to one, short line, trapezoid. Boom and boom. Many inputs. Let us see. Let us choose 4. Say I do 4 to 1. 1, 2, 3, and say 4. Four inputs, one output. So I'm going to call this guy my 4 to 1 mux. 4:1 multiplexer, whatever you want to call it. Let me name the inputs. Since these are data inputs, I'm going to call them D0, D1, D2, D3. And I'm going to call my output F, output of the multiplexer. So you have data inputs and you have the data output. What are we missing? We are missing select inputs. So tell me, how many bits do I need to select between 4 things? You would need 2 select inputs. Yes, because I'm selecting 1 out of 4. So exactly the same thing that you did for Studio 4. You are trying to push the output of the adder, XORer, ORer, or ANDer. So you were selecting 1 out of 4. So you needed 2 bits for the control input. Exactly the same here. So you would need 2 select lines. So let me draw them maybe in black again at the top. 1 and 2. And I will name them in blue. Say I have S1, my most significant select line, and S0, my least significant select line. Who knows what the numbering is? Well, the S1 and S0, the numbering itself should signify which one is most significant and which one is least significant. All right, what about these variables here? D0, D1, D2, D3. Well, later on we will see that you could have binary variables here. You could have logic expressions go in here, or you could have 0 go in here, low, or you could have 1 go in here, logic 1. So the D0, D1, D2, D3, those are data inputs. They could be 0, they could be 1, they could be binary variables as A, B, C, or they could also be A and B or C, like they could be expressions going into each one of the inputs. And depending on what the select line is, output F will equal one of those 4 choices. So actually let's write some statements over here to indicate the functionality of this 4:1 mux. So I'll say this. When S1 equals S0 equals 0, so both the select lines are 0, then F equals D0. How do I indicate that on the diagram? Well, I come in here and say when S1 is 0 and S0 is 0, I am going to allow F to be D0. Next, which one is least significant? S0 is least significant. Then this, then this. So similarly, I can write this as when S1 equals 0, S0 equals 1, F equals D1. Similarly, F equals D2. And last one, S1 equals 1, S0 equals 1, F equals D3. That's it. Those 4 statements completely indicate what this 4:1 mux is supposed to be doing. All right, questions about this slide. A very generic description of a mux. So like we have variables or expressions or 0 or 1 as our data inputs, similarly for S1 and S0, you can have 0 or 1 individually for each of these two, or you could have binary variables control them. We'll see those examples as well. All right, so let's move on here. Our first exercise moving forward is going to be to design a 2-to-1 mux. So I have two inputs here. Let's call these two inputs, say A here, B here. I have my select and I have my output F. So what's the description? The description is when S equals 0, I want my output to equal A. And when S equals 1, I want my output to equal B. So imagine this. I will highlight this in yellow, and that yellow is essentially this. Maybe I do it here. F equals A. And the other case, blue, you have this. F equals B. All right. I hope that is helpful. Now let's go on and do the following. Truth table followed by K-map followed by logic diagram for a 2-to-1 mux. So I need to find out what is inside this trapezoid. What is inside this symbol? Are there logic gates in it? Yes. Let's try to figure those out. What are my inputs? S, A, B. So I will use S here, A here, B here. Doesn't matter. You could switch the inputs. The order of the inputs doesn't really matter. And then the output column is F. So because I have 3 inputs, I'm going to have 8 combinations. 0, 1, 0, 1, 0, 1, 0, 1. And 2 zeros, 2 ones, 2 zeros, 2 ones. And then 4 zeros and 4 ones. Now, I'm going to use the statement here. When S equals 0, F equals A. All right, let's do that. We were doing this in yellow, right? All right, let's do that in yellow. When is S 0? Here. So F equals A. What is A? 0, 0, 1, 1. Next. S equals 1, F equals B. Those are the next 4. That's B. 0, 1, 0, 1. Done. That's my truth table for the 2-to-1 mux. And from this, I can start implementing the logic diagram. But I want to simplify it first so that I have few things to deal with. So I would need a three variable K-map. Let us quickly sketch that out. Maybe okay, I can draw it here. Oh, come on. Okay, S, A, B, 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1. All right, where do I have zeros? 0, 0, 1, 1, 0, 1, 0, 1. All right, based on this, it looks like I have a group right here, and I have a group right there. So this guy is going to be what? This is going to be S complement and A. and for this guy is going to be S and B. So with this, the logic expression is going to be F equals S complement and A, or S and B. Now, because we are color coding things, oh, sorry, that would be the blue one and that would be the yellow one. When S is 0, A goes through. When S is 1, B goes through. All right, questions so far? I still need to draw the logic diagram, but I think, given the logic expression, I think you guys will be able to quickly draw that up. I will do it in a moment. All right, let me add a page here to draw the logic diagram. Two to one. So let's see, I have F equals S complement and A, or S and B. So I'm going to have S and then S complement right here. Then I will have AND gate, another AND gate, OR gate, for the first AND gate I need S complement and A. For the next one I need S and B. That's it, that's F. So at this point I have S complement and A. At this point I have S and B. That's it. So what you see is, in terms of a symbol, you see that SABF, SABF, and inside that you have this. Now, you can actually make this a little bit more interesting by saying, okay, let's convert to NAND only, right? Bubble, 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 and you have a NAND only version. All right. Questions here? Another way of thinking about a multiplexer or a multiplexer is to think about using switches, right? Because switches allow connections to happen or disconnect between 2 points. So in this diagram, we are saying, what if you didn't have 1 bit for the data inputs? What if you had more than 1 bit for the data inputs? So as you can see here, earlier we had D0, D1, D2, D3. Those are all 1 bit each. But those inputs could also be multiple number of bits. So in this case, how many data inputs do you have? Well, you have n data sources. So D0, D1, D2, D3, so on up to Dn minus 1. So 0 to n minus 1 makes it n data sources. And each data source or data input is how many bits? B bit. So in this case, you are essentially selecting one out of this, or at the end this. So the output also needs to be B bits. As you can see here, it is B bits. So there is only one output, but that particular output is B bit long. You have select line, select lines indicated by S. So you have S bit select lines and you have an enable to enable the multiplexer. So let us see how this select is supposed to work. If you know that there are n data sources, how many select lines do you need? If you have 4 data sources, you would need 2 select lines. If you have 8 data sources, you would need 3 select lines. If you have n data sources, you would need log n to the base 2 select lines. In other words, the number of data sources n will equal 2 raised to s, where s is this guy, the number of bits for select. And enable is just one pin. So if it's enabled, it's enabled. Now you can think of all of that in terms of a switching exercise. So you see this, I'm going to color code D0 is one data input which is split into many. So the first bit of data input 0, the second one for data input 0, the bth bit of data input 0. So if you select based on this input select, let me use blue here. Select is select. If you select data input 0, then what is going to happen? Well, the first bit from here is going to go through, here going to go through, here going to go through, and then if it is enabled, this connection is made, if enabled, and then what would be y? Y would be D, first bit of D0, second bit of D0, and so on up to bth bit of D0. So that will be y, which is simply saying y equals D0. Now let's go on to the next one. What if the select lines were to select D1? What would happen then? Well, the first bit of D1 will go through, second bit of D1 will go through, and so on up to the bth bit of D1 will go through. If enabled, that will be the output. So essentially you can think of a selector over here or a commutator that is picking out each bit coming from the n data sources. So the first one is, let's see, the first one over here is selecting the 0th bit of all data sources, right? Which 0th bit will go through? Which, well, 0th bit, maybe I say first bit. One D0. And then so on. The last one will be selecting the bth bit of all sources. All right, questions about this? For the sake of completeness, let me say, you see this BD0. What is BD2? What does that mean? That means it is the bth bit of second, or not second data source, I can just say of D2 data source. So there are B switches, one for each bit of the input. There are B switches, that is correct. So that if you think about one switch here, so on up to B, those are B switches. Yes. Plus there is an additional B switches for the enable. Not N switches. No. So you don't have N switches. You have B switches, but that switch moves in N different locations. So each switch can have N different positions, but there are total of B switches. All right, let's move on. Can I make, so over here you have the symbol of 2:1 mux, 4:1 mux, and 8:1 mux. And all these muxes are 1-bit data sources. So here is a 2:1 mux where A is your select and A is selecting between I0 and I1. Over here you have a 4:1 mux where you have two select lines, A and B. Those will allow Z to be either I0 or I1 or I2 or I3. Similarly, you have a 8:1 mux. Select lines A, B, C. Inputs, data sources, 8 of them, I0 all the way to I7. The output Z. So Z can be one of these depending on what A, B, and C are. So just the symbols of 2:1 mux, 4:1 mux, 8:1 mux, and of course, muxes can be larger than that, 16:1, 32:1, and so on. An interesting question that I hope some of you or if all of you should be asking right now is, what if I don't have 8 inputs? What if my design only has 5 inputs? What should I do? Any ideas about that? What if I have only 5 inputs? What should I do then? Alex, you are right. We are going to get there in just a minute. Yes. This is where we are going with this. So the question right now is, what if I have only 5 inputs? What should I do then? Can I use a mux or not? Michael, you're right. So disable the additional ones. I wouldn't call it disable. I would just say don't use the additional ones. So if you have 5, suppose you have 5 data sources, clearly 4:1 mux is not enough. So you would have to go for 8:1 mux. So what you would have to do is you use these 5 and then you simply don't use the other 3. So leave them unconnected. Or you could in fact do this too. 1, 2, 3, 4, 5, and then leave these guys not connected. It's up to you. You can use any 5 out of the 8 available. As long as you set the select lines appropriately, you will be fine. Yes, you could use a 8:1 mux, but the additional inputs will need to be disconnected or not used. I won't say disable just because there is an enable to the overall mux, so it has to be enabled. But I would say not connected, so I can leave those inputs not connected. All right, let's move on here. Can I cascade muxes? Yes. Over here we are showing how to build an 8:1 mux using 2 4:1 muxes and 1 2:1 mux. And the simple criteria is this: select one from the top 4 inputs, select one from the bottom 4 inputs, and then select one of those two that were selected earlier. So that is a way to build bigger muxes using smaller muxes. So let us do this exercise here. What happens when let's say I have A as, so I'm going to make A as 1, and I'm going to make B as 1, and I'm going to make C as 0, and I'm going to see what happens for Z. What is Z in this case? All right. So A is 1, which means this guy is good to go. Next, I have B as 1 and C as 1. A was 1 here, B was 1, C is 0, sorry. So if B is 1 and C is 0, notice B is the most significant select, right? B is the most significant select, S1. So if it is true, you are talking about this as 1, 0. So which one will go through? Well, 1, 0, that's 2. That will go through. On the bottom one, what will go through? 1, 0. 6 will go through. And then because A is 1, what is Z? Now I think you guys will be able to tell me what Z will be. So the first stage was to select one out of the top 4. We selected I2 here and we selected I6 here. Then we said, okay, let us select one out of that. A was 1, so we selected I6. Yes, I6 is right. All right, so let's see. This is a overwhelming diagram, but it's actually, pretty simple to follow it. So let us try to see what is going on over here. It is a 8:1 multiplexer, right? This is a chip 74X151. 8 input multiplexer. So you're selecting 1 out of 8. How many select lines would you need to select 1 out of 8? Well, you need 3. What are those 3? Let us highlight them in blue. They are these. Those are my 3 select lines that are indicated over here as A, B, and C. Too big. 3 select lines. It also has an active low enable, and then it has 8 inputs, D0 all the way to D8, D6, sorry, D7, D0 to D7. Where are those 8 data inputs? Right here. Over here you have an active low enable. So let us try to write an expression here for the first guy. So let us suppose I have enable, this pin is 0. So that means I'm enabling it, which means this is 1, right? Sure. So what is the expression here? You have enable, which is 1. So that's, I will leave that out for now. Followed by D0, right? From here, you have D0 coming in. After that, what do you have? 3 inputs that are coming from all the way to at the bottom, if you see, those are from A complement, B complement, and C complement. So that is A complement, B complement, C complement. Next, what do you have? You have D1 ANDed with, you see here, let's see which one is the least significant is what I'm trying to figure out. This guy gets A. And if you can keep going down, you will keep going down here. So what does that mean? That means that if A was 0 and B was 0 and C was 0, D0 would go through. And once you select, so this is an OR gate, right? Think of it as an OR gate. And then once you put the bubble, you are saying you can have a active low output. And then you invert it again, you have an active high version available as well. So you have both true and complement forms of the output that are available, y and y underscore l. They are obviously supposed to be complements of each other, but this chip gives you both options: output in true form and complement form. Let us write that. Yes, A is least significant input, yes. And the way I find that out is by noticing this. If you see how A is connected, A complement goes in here, 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 and A goes in here, 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 here. So you see what is happening? 0 1 0 1 0 1 0 1 0 1, repeating the fastest, so least significant. So you're right. Let us just put it over here. Least significant input. Least significant, I should say select input. And obviously then C will be most significant select input. Right? So you are enabling the chip using the active low enable. Then you have 8 of those data sources going into the AND gates, and then 3 of those AND gates, the 3 of the inputs of those AND gates are corresponding to A, B, and C. So depending on which what A, B, and C are, only one of them will go through. So for example, if A is 0 and B is 0 and C is 0, D0 will go through because all of this will be 1 in that case. So this wire will be D0. All the others will be what? Well, of course, there will be zeros, right? Because A is 0 there. All the others will be 0. And then you have an OR gate here, followed by an inverter. And then you have another inverter there. So Y, in that case, will equal D0. Y underscore L will equal D0 complement. Right? So it's the same job. You change ABC, you change the input that goes through the output, and in this case, output is available both in true form and complemented form. All right, questions about this? So it looks a little bit scary up front, but it's not that difficult to navigate through it because it's based on a pattern, right? Okay. Next, we have a truth table for 74x157. This multiplexer is a 2-input multiplexer where each input can be 4-bit each. So let us try to actually draw a symbol here that will help us. So I'm going to draw a trapezoid just as I do earlier, and then I will select, I'll have 2 inputs, one right there, the other right there. I need 1 bit to select between them, and my inputs are 4-bit. So this guy is 4, this guy is 4, and obviously that has to be 4. And when S is 0, F equals, say, D0. And when S is 1, F equals D1. So that's kind of the symbol what we are talking about here. 2 input, let us highlight those inputs. This is 2 input, right? Where are the 2 inputs? D0 and D1. 4-bit. So in a form of a truth table, you can look at it like this. Inputs, you have an active low enable and you have a select. And the outputs, you are writing the outputs in the form of the inputs. So you have 4 outputs, the first bit of Y, the second bit of Y, the third bit of Y, and the fourth bit of Y. We have just written F here instead of Y. Okay, so to avoid confusion, I will use the same letter here. D0 and D1 are consistent, S is consistent, and I'm assuming that it is enabled. Okay. Next, if it is disabled, right, that is disabled. No matter what the select line says, the outputs are going to be 0. Then when it is enabled, if you select 0, D0 will go through. If you select 1, D1 will go through. So that's another chip, the 74X157. It is to select 1 out of 2 inputs, but each input is can be 4-bit. Now this same multiplexer is sketched on this slide in detail. So the inside of the multiplexer are being discussed now. It has to be enabled, right? There's an active low enable. Let us point that out. Where is the active low enable? Let's go back here. Active low enable on pin number 15. Active low enable on pin number 15. And then you have the select line on the next pin. All right, so let's assume that you have, let's make this enabled. So let's make this guy active low. And let us say we have S selected as 0, right? S can be 0 or it can be 1. I'm just assuming that it is 0 right now. So if it is 0, what would happen? This guy is 1 there. This guy is 1 there. That means this guy is 1 there. S is 0. So that means that is 1. That means that is 0. And this is 0 flipped. And that is 0. So the moment we have figured out those 2 lines for 1 and 0, what would happen? I can say this is 1, this is 1, this is 1, no, this is 1, and last one. And then what about the others? 0 and 0 and 0 and 0 and 0. The moment you see that all right, let me 0 0 0 0 0. The moment one of the inputs of the AND gate is 0, you know the output is 0, right? So the moment output is 0 and then that is feeding into the OR gate, that means this doesn't even matter. All that matters is the top input now. So what would this be? For example, it'll be 1D0, the first bit of D0 ANDed with 1, which is the same thing. Over here, it'll be 2D0. Over here, it'll be 3D0. And then over here, it'll be 4D0. Yeah. That will be the same as Y because the others are out. So this will be, so in that case, Y will equal D0. All 4 bits. And then, of course, if you switch it around, if you say, all right, S is 1, all the X's, all the zeros will become ones here, ones will become zeros here, and then you will, in fact, select the other input, D1. Where have we seen this before? Where have we seen something like this before? Two AND gates feeding into an OR gate, and the two AND gates are getting input S complement and S. Where have we seen that before? We have seen that before in the form of a 2:1 mux, right here. So literally in that chip, what we have is 4 2:1 muxes that are implemented there, 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 and there. All right, questions about this? Okay, let us move on to a very, very interesting application of the multiplexer. So we can implement a logic function using NAND gates only. We can implement a logic function using NOR gates only. We can implement a logic function using decoders. And we are going to add multiplexers to it. So we can also implement logic functions using muxes. So today we are going to, in the remaining time, we are going to focus on how to synthesize any logic function using a mux. So over here we have a function which is represented in canonical sum of products form. So the inputs are A, B, C. A obviously is the most significant input and C is the least significant input, and you have min terms that are given to you. Min terms that are 1 are 0, 1, 3, and 7. And we are asked to implement this function using 8:1 mux. Believe it or not, this is a very, very simple exercise. So let's see how this works. I have ABC in my truth table. So maybe I can take the canonical sum of products form and transition that into a truth table very quickly. So let's do that. So I have for C, I'm going to go, let's see, 0, 1, 0, 1, 0, 1, 0, 1. And for B, I'm going to go 2 zeros, 2 ones, 2 zeros, 2 ones. And then for A, I'm going to go 4 zeros and 4 ones. And because I know the row numbers that are going to be a 1, min terms 0, 1, 3, and 7. So let's do that. 0, 1, 3, 7. Everything else is a 0. 0 here, 0 here, 0 here, 0 here. So that's the truth table of uh, the function f. If I'm supposed to use 8:1 mux to synthesize this, then all I really need to do is use A, B, C as my select lines in that particular order. A here, B here, C here. And I'm going to write inside that this is the most significant select, this is the next one, and that is the next one. And when A, B, C are 0, 0, 0, and 0, 0, 1, and 0, 1, 0, and 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. What goes through? Well, all I have to do is simply copy this guy and paste it over here. Done. And that's my F. So literally all I had to do for a 8:1 mux is to put that output column directly as the inputs. And as you can see, what happens. If A is 0, B is 0, C is 0, F will equal 1, right? Because that will go through. Is 1? Yes. And you can pick out any over here, any row over here and verify it. So use the inputs as the select lines and use the output column as the inputs. All you have to do is be careful about the order of the input, order of the select inputs, right? So A was the most significant select, and we could do it very, very easily because A was also the most significant input to the function. All right, questions about how to synthesize a 3-input function f using a 8:1 mux. The next thing that I'm going to do is I'm going to try to synthesize the same function, but I'm going to use a 2:1 mux to do this. Now, in order for me to do this, I need to leverage Shannon's expansion theorem. Something new. So I'm going to first write my function f in the long form. So I'm going to write out all the 4 minterms. I have A, B, C, or A, B, C, or A, B, C, or A, B, C. 0, bar, 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 1, 0, 0, 1, 3, 0, 1, 1, 7, nothing. All right, so I've written out my canonical sum of products expression completely, not in shorthand, completely. Now, the first thing that I'm going to do is I'm going to ask one of you to volunteer and pick one between A, B, and C as the select variable. So I need, all right, Alan says C. Alan has volunteered and he says, I want to pick C as the select variable. Okay. So once I select C, so Alan says C. the next step is going to be this. I'm going to rewrite the same expression f in this form. I'm going to write this as C complement ANDed with some logic expression, and I need to figure out what goes inside those square brackets, or C with another function. Now my goal is, while I do this, my function has to remain the same. And I need to figure out what goes here and what goes here. As long as this function is the same. So tell me, where do you see C complement? All right, I see a C complement there. I see, that's it, only one C complement. So what should go inside the first square bracket? A complement and B complement. Yes. Next, where is C? C is here and here and here. All right, a lot of them. Let us write what goes inside the next one. There is a complement, B complement, or A complement, B, or A or B. All right, but maybe I can simplify this a little bit further. How can I do that? I'm going to use my Boolean algebra tricks a little bit to simplify this. One more step. I see an A complement that is common between the first two terms. Actually, I think this is one of the 17 or 17D, I think, will apply to this. I think it's a consensus theorem, but we will do it. A complement, if you fill that out, A B complement or B, or A and B, okay, which is also equal to A complement or AB, which equals A complement or B. So from here to here, I went using 11D. So A complement or B is the simplest expression there. So this is how I would implement this function using 2:1 mux. What did Alan pick for the select variable? Alan picked C, so that becomes the select. When C is 0, A complement, B complement goes through. When C is 1, A complement or B goes through to F. And notice where we are getting this from. Let us see, green here. That is the top input. And that is the bottom input. So we have used a 2:1 mux to synthesize the same function. Now I hope I would encourage you guys to verify this. So what happens? So let me write a few statements about this. If C equals 0, then F equals A complement and B complement, right? That's the claim here. And when C is 1, F is A complement or P. That's the claim here. Can I verify this? Sure. Just go back to the truth table and see what happens if you put C as 0, what happens? You can check when C is 0 for those 4 places, is F A complement and B complement or not. You can quickly check that. How? Let us make a truth table for A, B, and F when C is 0, right? So when C is 0 means here, 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 and here. So what is A and B then? 0, 0 for the first case, 0, 1 for the second case, 1, 0 for the next one, 1, 1 for the last one. What is F? 1, 0, 0, 0. So what would be the F? It would be A complement and B complement. Checks out. So you can quickly verify this for this guy as well as for the next one. All right, questions about how to synthesize a function using an 8:1 mux and a 2:1 mux. And the next step that we are going to do, if you can bear with me with time, is the same function but using the 4:1 mux. So what I'll do is I'll start where I left off. In the previous example, because it's the same expression, I will start where I stopped. I stopped here. In the previous one, I had until here. No, not this. It is A complement or B. So this is where I stopped earlier on the previous slide, right here. I will get to you guys, get to your questions in just a minute, you guys. Now I need another select line because I have 4:1 mux. I need another select line. So apart from C, can somebody volunteer and pick one more select? And now you have only one A or B as your choice. Pick one more select between A and B because C is already taken. All right, Alan says A. All right. Let's do this. Now my goal is going to be to write the same function but in this form. C complement remains as is, but inside C complement and C, I'm going to use a trick, which is to use Shannon's expansion inside those square brackets. So I'm going to have A complement or A complement or A. I'm using A here because Alan picked A as the next select variable. So what goes in here? So you see all of this should equal all of that. And all of this should equal all of that. So let's try to figure out what goes in here. Well, only B complement, this guy is 0. You guys agree with that? Because the moment this guy is B complement, it matches up, and this guy has to be 0 because there is no term with A. Now let's try to match up the green ones. A complement, okay, so that means that this has to be 1. Now here is a kicker. B doesn't have A complement, so where does it go? Because B doesn't have A and it doesn't have A complement, it actually goes in both. So I would have to do OR B and B. It goes in both. I hope you see that. It goes in both. And I can quickly verify this. All I'm saying is B equals A complement and B or A and B, right? So I'm putting this guy right here, and I'm putting this guy right here. All right, so what is 1 or B? Let's simplify. 1 or B is 1, B is B. That's it. I can't simplify anything else. So now I'm ready to synthesize it using the 4:1 mux. What was our first select line? It was C. Alan picked C first. What was our second select line? Alan next picked A. So this is our most significant select. This is our least significant select. Output is F. What goes? So this is 0, 0. This is 0, 1, 1, 0, 1, 1. So when C and A are 0, 0, what happens? B complement goes through. So the now is going to be, let me highlight these guys as not this, maybe this. Top, next, next, next. B complement 0, 1, B. Done. This is how you would synthesize the same function using 4:1 mux. So we have learned how to synthesize a 3-input function using 8:1 mux. We synthesize the same function using 2:1 mux by applying Shannon's expansion theorem one time. And then we went on to synthesize the same function using 4:1 mux by applying Shannon's expansion theorem one more time. And while we were doing that, wherever necessary, we were simplifying things out. All right, so I hope that was helpful, you guys. We will stop here. Now, the last few minutes, I wanted to complete this exercise, which is why I was kind of ignoring your questions on the chat box. I will get to that in just a minute, but I would encourage you guys to watch this Shannon's expansion, the mux application for logic functions, maybe one more time after this gets posted on YouTube. I think it'll be very helpful. All right, so I'll stop the recording now.